Hello children. ਅੱਜ ਦੇ ਲੈਸਨ ਵਿੱਚ ਅਸੀਂ NERNST equation and concentration cells ਬਾਰੇ ਸਿੱਖਾਂਗੇ. In electrochemistry, the NERNST equation is an equation which can be used to determine the equilibrium reduction potential of a half cell in an electrochemical cell. It can also be used to determine the total voltage, that is electromotive force, for a full electrochemical cell. ਇਹ ਨਾਮ ਜਰਮਨ ਫਿਜ਼ੀਕਲ ਕੈਮਿਸਟ ਵੋਲਥਰ ਨਰਸਟ ਦੇ ਨਾਂ ਤੇ ਰੱਖਿਆ ਗਿਆ, ਜਿਸ ਨੇ ਇਸ ਨੂੰ ਸਭ ਤੋਂ ਪਹਿਲਾਂ ਫਾਰਮੂਲੇਟ ਕੀਤਾ. ਟੌਪਿਕ ਨੂੰ ਅੱਗੇ ਵਧਣ ਤੋਂ ਪਹਿਲਾਂ ਅੱਜ ਦੇ ਟੌਪਿਕ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਬਾਰੇ ਜਾਣ ਲਈਏ.
On completion of this topic, learners will be able to discuss NERNST equation, solve numerical related to NERNST equation, calculate EMF of the cell with the help of NERNST equation, study concentration cells, deduce equilibrium constant from NERNST equation.
The standard electrode potentials are measured in their standard states when the concentration of the electrolytes solutions are fixed as 1 molar and temperature is 298 Kelvin. But in actual practice, electrochemical cells do not have always fixed concentrations of the electrolyte solutions. The electrode potentials depend on the concentration of the electrode solutions. NERNST gave a relationship between electrode potentials and the concentration of electrolyte solutions known as NERNST equation. Have a look at the general electrode reaction on the screen. N plus ions in aqueous state accept Ne electrons to form metal in solid state. The electrode potential at any concentration measured with respect to standard electrode potential can be represented by equation shown on the screen. Electrode potential under given conditions is equal to electrode potential under standard conditions minus gas constant R multiplied by temperature divided by number of electrons involved in the reaction multiplied by Faraday's constant F multiplied by natural log molar concentration of the metal divided by molar concentration of ions. But concentration of solid M is taken as unity. So we have the next equation shown on the screen, which shows electrode potential under given conditions is equal to electrode potential under standard conditions minus 2.303 multiplied by R multiplied by temperature divided by number of electrons involved in the reaction multiplied by F multiplied by log of molar concentration of the metal divided by molar concentration of ions. To convert natural log to the base 10, we multiply with 2.303. As a result, ln(x) is equal to 2.303 log x, where E Mn plus upon M is equal to electrode potential as shown on the screen, and E naught Mn plus upon M is equal to standard electrode potential for 1 molar solution of metal ions. Given that R is gas constant having value 8.314 joules per Kelvin per mole, F is Faraday's constant having value 96,500 coulombs, T is temperature in Kelvin, and Mn positive is the molar concentration of the species. M represents molar concentration of the metal. Substituting the values of R, that is 8.314 joules per Kelvin per mole, temperature, that is 298 Kelvin, and F, that is 96,500 coulombs, the NERNST equation can be written as shown on the screen. This means that electrode potential under given conditions is equal to electrode potential under standard conditions minus 2.303 multiplied by 8.314 multiplied by 298 divided by number of electrons involved in the reaction multiplied by 96,500 multiplied by log of molar concentration of the metal divided by molar concentration of ions. Simplifying the equation, we get electrode potential under given conditions is equal to electrode potential under standard conditions minus 0.059 divided by number of electrons involved in the reaction multiplied by log of molar concentration of the metal divided by molar concentration of ions. Let me tell you here that concentration of the solid phase is taken as unity. The equation which we have learnt just now can also be rewritten as shown on the screen. This means that electrode potential under given conditions is equal to electrode potential under standard conditions minus 0.059 divided by number of electrons involved in the reaction log 1 divided by molar concentration of ions in aqueous solution. Children, at 25 degrees centigrade, we can also write this equation which we learnt just now in simple form as shown on the screen. So, ਅਸੀਂ ਹੁਣ तक ਇਹ सब सीखा है. With the help of NERNST equation, we can calculate the reduction potential of an electrode at given concentration of the ions in solution provided its electrode potential under standard conditions is known. Children, आओ हुन कुछ problems नो solve करिए. Question is, zinc rod is dipped in 0.1 molar solution of zinc sulfate. The salt is 95% dissociated at this dilution at 298 Kelvin. Calculate the electrode potential given that standard electrode potential for zinc is minus 0.76 volts. And the answer is the electrode reaction is as shown on the screen. This means that zinc ions accept 2 ions to form Zn metal in solid state. This reaction is reversible. According to the NERNST equation, at 298 Kelvin, electrode potential of zinc under given conditions is equal to electrode potential of zinc under standard conditions minus 0.059 divided by number of electrons involved in the reaction multiplied by log of molar concentration of the zinc metal divided by molar concentration of zinc ions in aqueous phase. Substituting the values of standard electrode potential of zinc is equal to minus 0.76 volts and concentration of zinc as 1 in the equation we get. Concentration of zinc ions in aqueous state is equal to 0.1 multiplied by 95 divided by 100 multiplied by log 1 upon 95. This means that electrode potential under given conditions for zinc is equal to minus 0.76 minus 0.059 upon 2 multiplied by log 1 upon 0.095, which is equal to minus 0.76 minus 0.03, which is equal to minus 0.79 volts. Children, आओ हुन एक और problem solve करन दी कोशिश करिए. If E naught for copper electrode is plus 0.34 volts, how will you calculate EMF value when the solution in contact with it is 0.1 molar in copper ions. ਹੁਣ ਅਸੀਂ ਇਸ ਦਾ solution ਕੱਢਣ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਦੇ ਹਾਂ. EMF of the cell can be calculated by using NERNST equation as shown on the screen. Copper ions get reduced by accepting 2 electrons to form copper. NERNST equation ਦੇ ਅਨੁਸਾਰ electrode potential under given conditions is equal to electrode potential under standard conditions minus 0.059 upon 2 multiplied by log 1 upon concentration of copper ions. When concentration of copper ions is 0.1 molar, electrode potential under given conditions is 0.34 minus 0.059 upon 2 multiplied by log 1 upon 0.1, which is equal to 0.34 minus 0.059 upon 2 multiplied by log 10, which is again equal to 0.34 minus 0.059 multiplied by 1 divided by 2. This is equal to 0.34 minus 0.0295, which is equal to 0.31 volts. ਹੁਣ ਅਸੀਂ applications of NERNST equation ਬਾਰੇ ਪੜਾਂਗੇ. Children, let us now learn about calculation of cell potential using NERNST equation. Let us discuss about this calculation by taking into consideration a Daniell cell in which the concentrations of the solution may be 1 molar. Let us represent the cell as shown on the screen. Zinc half cell, salt bridge, copper half cell. The EMF of the cell is standard reduction potential of cathode minus standard reduction potential of anode, which is equal to, the electrode reactions can be written as shown on the screen. Zinc loses 2 electrons to form zinc ions. Copper ions gain 2 electrons to get reduced to copper. The electrochemical cell reaction can again be written as shown on the screen. Zinc in solid state reacts with copper ions in aqueous state to form zinc ions in aqueous state and copper in solid state. The electrode potential for the 2 electrodes can be calculated by using NERNST equation as electrode potential for copper electrode. Electrode potential of copper under given conditions is equal to electrode potential of copper under standard conditions minus 2.303 divided by 2F multiplied by log of molar concentration of the copper metal divided by molar concentration of copper ions in aqueous phase. Similarly, electrode potential for zinc electrode. Electrode potential of zinc under given conditions is equal to electrode potential of zinc under standard conditions minus 2.303 multiplied by R multiplied by T divided by 2F multiplied by log of molar concentration of the zinc metal divided by molar concentration of zinc ions in aqueous phase. Substituting the values in the equation shown on the screen, we get EMF of the cell as equal to EMF of copper half cell minus EMF of zinc half cell. This can also be represented as EMF of the cell is equal to standard electrode potential of copper minus standard electrode potential of zinc minus 2.303 multiplied by R multiplied by T divided by 2F multiplied by log of concentration of copper metal multiplied by concentration of copper ions in aqueous phase divided by concentration of copper ions in aqueous phase multiplied by concentration of zinc metal. Now we know that standard electrode potential of copper minus standard electrode potential of zinc is equal to EMF of the cell, and the concentration of solids is taken as unity, so that concentration of zinc metal is equal to 1 and concentration of copper metal is also equal to 1. Therefore, we can say that EMF of the cell is equal to standard potential of cell minus 2.303 multiplied by R multiplied by T divided by 2 multiplied by F multiplied by log of concentration of zinc ions in aqueous state divided by concentration of copper ions in aqueous state. Since 2.303 multiplied by R multiplied by T divided by F is equal to 0.059 at 298 Kelvin, thus we have at 298 Kelvin. EMF of the cell is equal to standard potential of cell minus 0.059 divided by 2 multiplied by log of concentration of zinc ions divided by concentration of copper ions. In the Daniell cell, the valences of zinc and copper are the same, that is N is equal to 2. Let us consider an example in which the valences of the two metals used in the two half cells are not same. Consider the cell as shown on the screen. Copper electrodes in copper ions, salt bridge, silver ions. The cell reaction is copper in solid state reacts with silver ions in aqueous state to form copper ions in aqueous state and silver in solid state, and the EMF of the cell is standard reduction potential of cathode minus standard reduction potential of anode. During the reaction, 2 electrons are released by one copper atom, but 1 electron is accepted by silver ions according to the reaction shown on the screen. To balance the loss and gain of electrons, the reduction half cell is multiplied by 2, so that the net reactions are: copper in solid state releases 2 electrons to form copper ions in aqueous state. Silver ions in aqueous state accept 1 electron to form silver metal in solid state. The electrode potential of 2 electrodes may be written according to NERNST equation as electrode potential for copper electrode. We will now discuss about electrode potential for silver electrode. In the given cell, 2 silver ions are reduced to silver metal for every copper atom getting oxidized to copper ion. Hence, to equate the number of electrons, the concentration of silver and silver ions in the equation will be squared. It must be remembered that E naught of silver ions with respect to silver remains unchanged. Substituting the value in the equation as shown on the screen, copper half cell, salt bridge, silver half cell, we get EMF of the cell is equal to EMF of silver half cell minus EMF of copper half cell, which is equal to standard reduction potential of silver minus standard reduction potential of copper minus 2.303 multiplied by R multiplied by temperature upon 2 multiplied by F multiplied by log of concentration of silver metal raised to the power 2 multiplied by concentration of copper ion in solution divided by concentration of silver ion in aqueous solution raised to the power 2 multiplied by concentration of copper metal. Now, the difference between standard potential of silver and standard electrode potential of copper is equal to standard electrode potential of cell, and the concentration of copper and silver in solid state is unity. So, the equation becomes EMF of cell is equal to the standard potential of cell minus 2.303 multiplied by R multiplied by temperature upon 2 multiplied by F multiplied by log of concentration of copper ion in solution divided by concentration of silver ion in aqueous solution raised to the power 2. Since 2.303 multiplied by R multiplied by T upon F is equal to 0.059 at 298 Kelvin. Thus, we have at 298 Kelvin EMF of cell is equal to the standard potential of the cell minus 0.059 divided by 2 multiplied by log of concentration of copper ion in solution divided by concentration of silver ion in aqueous solution raised to the power 2. In general, for an electrochemical cell reaction, A moles of A reacts with B moles of B in presence of N electrons to give C moles of C and D moles of D. The NERNST equation may be written as EMF of the cell is equal to standard electrode potential of cell minus R multiplied by T divided by N multiplied by F natural log of equilibrium constant Q. Or we can say that EMF of cell is equal to standard electrode potential of cell minus 2.303 R multiplied by T upon NF multiplied by log concentration of C raised to the power C multiplied by concentration of D raised to the power D divided by concentration of A raised to the power A multiplied by concentration of B raised to the power B. Again, 2.303 RT upon F is equal to 0.059 at 298 Kelvin. Thus, we have at 298 Kelvin EMF of the cell is equal to standard electrode potential of cell minus 0.59 upon N log concentration of C raised to the power C multiplied by concentration of D raised to the power D divided by concentration of A raised to the power A multiplied by concentration of B raised to the power B. The value of A, B, C, D and N are obtained from the balanced cell reactions. Concentration cells. Concentration cells are special types of electrochemical cells in which the two plates of the same metal are dipped separately in two solutions of the same electrolyte also. These solutions have different concentrations. In other words, we can say that a cell in which both electrodes are of the same type but the solutions of the electrolyte in which they dip have different concentrations is called concentration cell. For example, consider a copper ion concentration cell in which copper electrode are dipped in two different concentrations C1 and C2. The two half cell reactions that are taking place are copper in metallic state loses 2 electrons in the oxidation half reaction. Copper ions accept 2 electrons to form copper in metallic state in the reduction half cell. The cell reaction can be represented as shown on the screen. Copper ions in C2 concentration plus in metallic state gives copper ion C1 concentration plus copper in solid state. The EMF of a concentration cell may be written as shown on the screen, which is equal to minus 2.303 multiplied by R multiplied by T divided by N multiplied by F multiplied by log of concentration of C1 upon C2, which is equal to 0.0591 upon N multiplied by log of concentration of C2 upon concentration of C1 at 298 Kelvin. C1 is equal to 0.01 molar solution, C2 is equal to 0.1 molar solution. For the cell shown on the screen, EMF of a concentration cell is equal to 0.0591 upon 2 multiplied by log of 0.01 molar solution divided by 0.01 molar at 298 Kelvin, which is again equal to 0.0295 multiplied by log 10, which is equal to 0.0295 volts. In this case, the standard electrode potential of the two electrodes will cancel and the cell potential is given as R multiplied by T divided by 2F multiplied by natural log C2 upon C1.
Have a look at the type of cell shown on the screen. In a concentration cell, molar concentration of the dilute solution increases and that of the concentrated solution decreases as the cell operates. At equilibrium, the two solutions of the electrolyte acquire the same concentration. The EMF may be represented as 0.591 upon N multiplied by log of C2 upon C1. Thus we see that at equilibrium, the concentration cell will stop working and will not generate EMF in case the concentration in the other two half cell become equal.
Children, आओ हुण सेल दे NERNST इक्वेशंस दे कुछ एग्जांपल्स नो स्क्रीन ते वेखिए. एल्यूमिनियम हाफ सेल, सॉल्ट ब्रिज, निकल हाफ सेल. सेल रिएक्शन ਨੂੰ ਇਸ ਤਰ੍ਹਾਂ ਲਿਖਿਆ ਜਾ ਸਕਦਾ ਹੈ. 2 moles of aluminium react with 3 moles of nickel ion to give 3 moles of nickel and 2 moles of aluminium ion. In this process, 6 moles of electrons are transferred. Hence, here N is equal to 6. The NERNST equation is again as shown on the screen. Electrode potential of the cell at 298 Kelvin is equal to standard potential of cell minus 0.059 divided by 6 multiplied by log of concentration of aluminium ions raised to the power 2 divided by concentration of nickel ions raised to the power 3. ਹੁਣ ਇੱਕ ਹੋਰ एग्जाम्पल ਲੈਂਦੇ ਹਾਂ. मैग्नीशियम हाफ सेल, salt bridge, silver half cell. The cell reaction is as shown on the screen. Here N is equal to 2. The NERNST equation is again as shown on the screen. Let us take another example. Zinc half cell, salt bridge, hydrogen half cell. Have a look at the cell reaction shown on the screen. Here N is equal to 2. Let us have a look at the NERNST equation at 298 Kelvin. Children, ਹੁਣ ਅਸੀਂ equilibrium constant from concentration cell ਬਾਰੇ ਜਾਣਾਂਗੇ. The EMF of a cell can be used to calculate the value of equilibrium constant in a cell reaction in the state of equilibrium. Let us consider the redox reaction taking place in a cell as shown on the screen. For this reaction, we have equilibrium constant Kc is equal to concentration of zinc ions in aqueous phase multiplied by concentration of copper ions divided by concentration of zinc metal multiplied by concentration of copper ions in aqueous phase. Since concentration of zinc ions is equal to 1 and concentration of copper ions is also equal to 1, thus using these values in the given expression we get Kc is equal to concentration of zinc ions in aqueous phase divided by concentration of copper ions in aqueous phase. The NERNST equation for the given equation is EMF of the cell is equal to standard potential of cell minus 2.303 multiplied by R multiplied by T divided by 2F multiplied by log concentration of zinc ions divided by concentration of copper ions. Since E cell at equilibrium is 0, the above equation becomes as shown on the screen. Generally, we have this equation which we are seeing on the screen, where N is the number of electrons transferred during the reaction. At 298 Kelvin, substituting the values of R as 8.314 joules Kelvin mole, T as 298 Kelvin and F as 96,500 coulombs in the given expression, we get equations which you can see on the screen. Thus, knowing the standard EMF of the cell, the equilibrium constant can be calculated. Students, ਹੁਣ ਸਮਾਂ ਹੈ ਅੱਜ ਦੇ ਲੈਸਨ ਨੂੰ ਦੁਹਰਾਉਣ ਦਾ। ਅੱਜ ਅਸੀਂ ਇਹ ਸਭ ਪੜ੍ਹਿਆ। Dependence of EMF on concentration of electrolyte and temperature, that is the NERNST equation. Calculation of EMF of the cell with the help of NERNST equation, concentration cells and equilibrium constant from NERNST equation. We also solved a few problems. आओ हुण एक होर प्रॉब्लम नु सॉल्व करिए। My first question is, calculate the reduction potential for the following half cell reaction at 298 Kelvin. Silver ions accept one electron to form silver metal. Given that concentration of silver ion is 0.01 molar and standard electrode potential is equal to 0.08 volts. And now here is the solution. According to NERNST equation, EMF of the cell is equal to standard electrode potential of the cell minus 0.059 divided by N multiplied by log 1 divided by molar concentration of ions in aqueous state. This can also be written as standard electrode potential of the cell minus 0.059 divided by N multiplied by log 1 divided by concentration of silver ions in aqueous solution. Given that standard electrode potential of the cell is equal to plus 0.80 volts, N is equal to 1 concentration of silver ions in aqueous solution is equal to 0.01 molar solution. By substituting the values in the equation, we get EMF of the cell is equal to 0.80 minus 0.059 upon 1 multiplied by log 1 by log 0.1, which is equal to 0.80 minus 0.0591, which is equal to 0.741 volts. This is because log 1 upon 0.01 is equal to 1. ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦਾ ਲੈਸਨ ਇੰਜੋਏ ਕੀਤਾ ਹੋਵੇਗਾ। ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਇੱਕ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ।